Welcome today to the Polymath World channel. I'm so excited about what we're going to be talking about today. We have a terrific guest here, and we're going to be diving deep into particle physics, high energy physics, and hopefully all kinds of other interesting and crazy stuff in between. I'm joined today by Professor Paul Heslop, who's Professor of Mathematical Physics at the University of Durham. Thank you so much for joining me today, Paul.
Thank you very much for having me. I'm very excited to be here.
Well, we just had a great chat a few weeks ago with Phil Halper, who co-wrote a book called The Battle of the Big Bang with 𝐂onnect. So we have been dealing in a little bit in gravity, and I'm hoping we're going to go even deeper into gravity today. So could you just tell me a bit about your background and how you got to be where you are today at Durham?
Sure, yeah. So I'm from England. I was born in Wolverhampton, moved around quite a bit. And I guess I was always enjoyed maths, from a very early age. I remember in kind of year 5, the head teacher took us out, took a few of us out to do some extra maths, and that kind of was partly inspired me, I think. And then I guess, when it came to sort of deciding what to do at university, I had this, I would do maths, I would do puzzles, hard maths. I wasn't always the quickest, or the most confident, actually, but I would, the harder problems I would stick at and keep going. And then I guess I also was interested in fundamental physics, more from kind of conversations with I guess started with my dad, who was previously a physics teacher, and then became a vicar. And then I sort of realized that the two actually went together. So I did a maths degree at Oxford, that was just in straight maths. But I always had in the back of my mind, maybe I can go on and do a more theoretical physics direction. And so then I went on to do part 3 in Cambridge, which is like their kind of master's course. It's the 4th year of the undergrad there, which I got funding to go on and do that. So that was kind of gradually going from the more maths area to the more theoretical physics. And then I decided to carry on and do a PhD. Things were going quite well. So I was fixed on London for sort of personal reasons. My then girlfriend, now wife, was in London. So I was looking at London, Oxford, Cambridge, sort of nearby. Nearly ended up doing the sort of formal quantum mechanics type stuff with Chris Isham. But I get always interested in the sort of quantum gravity type area, as we'll probably discuss. And but I went to King's College London with Paul Howe and worked on similar sort of stuff that I'm working on today, really, which we can go on and talk about. So yeah, and then it's the standard story in this field. It's quite hard. So. You do a PhD, and then you kind of have to do the mill. What's the word? Go around and do lots of postdocs usually. So I ended up doing 10 years or so of postdocs. That's a 2 or 3 year position. Can be anywhere in the world. I was reasonably lucky. I went to Germany for 3 years, and then I was back in the UK. I did a postdoc in Cambridge for 2 years, and then at Queen Mary for 2 years. Before getting the permanent position here in Durham. So it's quite, you have to kind of keep going if you want to keep going. But we can maybe talk about that a bit as well, if you like, yeah.
Yeah, it's not easy. You've mentioned a few inspirations there. You mentioned your father being a physics teacher. You mentioned your year 5 teacher. Was there anything else that sort of really gripped you in physics? You seem to have these two converging paths of maths and physics. With gravity, for example, were you just jumping off high buildings and things like that and going, I want to study?
Yeah, I guess I was reading some popular science books as well. So Roger Penrose was quite a big influence.
Yeah.
He's written some really great popular science books. I kind of the right sort of level, I say, sort of not too popular, but really getting to grips with things. They were very inspirational. Yeah, I think it was just my. I mean, I remember thinking to myself, I could do pure maths. I would be happy doing pure maths. I was sort of like, I liked the maths. I was good at the maths. But then I had this idea. Well, there's this fundamental physics, the laws of the universe, that are written in mathematics and that people look at. You know, people like Einstein and Newton. You know, that's really what they're doing. They're doing maths. So can I not kind of try and think towards that? And so I was going in that sort of direction. Yeah.
Yeah, I want to immediately ask a question which is off script here, because my doctorate is on Sir Arthur Eddington and Sir James Jeans, and they both passionately believed that the universe was written in pure maths. And
Right.
they were both mathematicians first who tended to mock the physicists for not being as fundamental as they were. Do you think, like Jeans and Eddington did, that maths is something we discover rather than something we create or invent? What's your take on that?
Oh, they thought that we discovered it, did they?
Yeah, that it's just a truth of the universe that we've discovered rather than a tool we've created or invented.
Oh, sorry. Yeah. No, exactly. I would completely agree with that. Completely. Yeah. Sorry, I thought it was the other way around. Yeah, absolutely. There's this feeling. I mean, you're certainly not inventing this stuff, and the people, different people come up with the same things, independently, and there's just. I mean, it's hard to sort of specify quite why, but it's definitely the feeling that you're discovering something that was already out there. I mean, these are truths. These seem to be fundamental truths.
Yeah.
Yeah, no, I find that sort of thing very fascinating as well.
Yeah, I can understand why. It's you mentioned Roger Penrose, one of the great mathematical physicists of his era, Nobel Prize winner. So you ended up not staying in pure maths alone, but moving into mathematical physics. Was that because there was a particular problem that you wanted to solve, or a particular issue you wanted to get your teeth stuck into?
Well, I suppose if there was a particular problem, it would be kind of quantum gravity that was really, I guess that's the big problem in theoretical physics in some sense. One of the big problems, and that's at the level that you can understand. I mean, it's also, it is very mathematical, that fundamental physics, and so even at an undergraduate level, even having done a master's, it's very hard to know what you precisely what you want to do. You really rely on your supervisor for that. But as far as I could say, what I wanted to do, it was definitely in the area of quantum gravity, and just in fundamental physics, just trying to understand what are the laws that govern the universe. And well, I mean, I'd happily go on and sort of describe the current status and the missing things, but I don't know. Maybe you want to.
Let's stick with quantum gravity. Could you explain it in layman's terms, and then sort of talk about your work in the field and your research there?
Right. Well, okay. So to talk about, I think I do need to talk a little bit about the general status of the field of fundamental physics. I mean, we basically have two theory. One specific theory, which is general relativity, which I think people will know about. Einstein theory of gravity, involving curvature of space-time. And then we have quantum field theory, which is more like a mathematical umbrella, but it's the mathematical theory that basically describes everything else at the fundamental level. So you've got the force of gravity, then you've got the three forces: the strong, weak, and electromagnetic force. But after huge amounts of work, we sort of pinned down the theory is quantum field theory, and within that there are specific particles. Collectively, this is known as the standard model of particle physics. So most of the particles we've all heard of, quarks and electrons and so on. And these two theories basically describe everything that one does in experiment to huge precision, accurately. They're sort of too good in some sense. They're too perfect. So you've got general relativity, you've got the standard model of particle physics. But they're kind of very different from each other. The general relativity is what's called a classical theory. It's not a quantum theory, so it's written in terms of definite objects, in this case, space-time. Whereas quantum field theory, you don't really talk about definite objects in the same way. You're just talking about probabilities of objects. A quantum field is not quite the same as a field. A field is something where you have a specific value at everywhere in space and time, whereas a quantum field is a quantum fluctuation over. You don't have a specific value until you measure it. It's this strange quantum world. So they're very, very different. Classical, general relativity, and everything else quantum. And of course, and the stuff that we actually measure, they don't really collide. So there's no kind of conflict there in terms of the experiments that we normally do, because general relativity is governing, the cosmology, if you like, what galaxies are doing and so on. Whereas the quantum field theory is more what is the LHC particle accelerator experiments doing, and there you can basically ignore gravity. But if you wanted to do some experiment inside a black hole, for example, or if you want to understand the Big Bang, then these two, so these are very highly theoretical, right? There's not things that we can actually do. So, a hard-nosed person might say, well, why do I care? These things work. I can measure things. It's fine. But we really want to understand what is going on. What is the universe made of? In principle, I can do an experiment, inside a black hole, and something should be happening. So, what is the mathematics? What is the theory behind that? And that's kind of what the idea of quantum gravity is. So, quantum gravity is just sort of a global term for how to reconcile these theories, the quantum theory and the gravitational theory.
Yes. Can I ask here, that is this moving into sort of theory of everything territory?
I guess so, very much so.
I mean, Arthur Eddington, who I did my PhD on, he spent the last 13 years of his life trying to come up with one and failed, and it basically ruined his reputation. Obviously, Einstein tried, David Hilbert tried. A lot of people have tried, and no one's succeeded. But do you think here this is maybe the best candidate, or something that's moving towards the right answer?
Well, you see, this brings us on to string theory, which is an important part of what I do. It's not necessarily directly what I work on, but string theory, in some sense, is a quantum theory of gravity. Now, there's various kind of caveats there, in that it's not necessarily a completely well understood theory, but the things that you can calculate in it agree with general relativity, in the sense that strings only propagate on backgrounds that agree with general relativity, and it also predicts this quantum particle of gravity, the graviton. So it seems to be a quantum theory of gravity that's just there for us, and people spend a lot of time trying to understand this theory for that reason. Now, you may be aware there's problems with it. And it doesn't seem to describe the actual universe that we live in. So it's a quantum theory of gravity, but whether it's our universe is hard to tell. It's a very big theory. So it's a very big theory with many different solutions. So in order to see whether our universe that we see fits in it is not that easy to tell. But so one of the big theoretical breakthroughs, which is kind of complicated to explain, which is why I think it's not as well known as it might be. It's called the ADS-CFT correspondence, and it's basically saying that, in the simplest terms, it's basically saying quantum gravity, a certain type of quantum gravity, is equivalent to a certain type of quantum field theory. Now, these are, as I said, quantum field theory is an umbrella theory, and the standard model is just a very specific example of that. So you've got our universe, you've got this big space of theories, you've got our universe, but you've got these sort of hypothetical universes or theories that you can look at. And there's one very special theory called N=4 super Young-Wells. It's not got a very exciting name, but it's known by some as the hydrogen atom of quantum field theory, because it's somehow got this sense that it's the fundamental quantum field theory. It's the most symmetric quantum field theory. And I study that for various reasons. One is just to try and understand a quantum field theory, the simplest possible one, as well as possible. Because although quantum field theory, we sort of, we understand the standard model, but actually computing things within quantum field theory is notoriously difficult. So we want to try and compute things in this theory. But it also has this beautiful thing, the ADS-CFT correspondence. I think I started talking about that before it cut out. And this relates this theory to quantum gravity theory, a specific string theory, in fact. So I did some computations a few years ago within this quantum field theory. Again, that's a theory we understand well, and that computes things for you in quantum gravity, a theory that we don't understand at all well. So we're able to do some specific computations in quantum gravity using the quantum field theory. That's one aspect of quantum gravity, if you like.
Now, you talk about quantum gravity. I noticed these things on your research profile and on your many publications. One of your main areas of research is supergravity. Now, what's the difference between gravity and supergravity?
Okay, no, very good. So I mentioned that this theory that I study is very symmetric. So one aspect of this is supersymmetry. So, which is just symmetry mathematically is kind of what we think of it. So symmetry, you think of a cube having reflection symmetry and rotation symmetry. But if you think about what it really means that I do some transformation on it. But after I've done something, it looks the same as it did to begin with. And that's what we mean by a symmetry, sort of more mathematically. So I do some transformation, but the thing is actually unchanged after I've done the transformation. And there are these weird symmetries called supersymmetries where you actually transform different types of particles. So you can transform fermions, which are the matter particles, things like quarks, into bosons, which are the force particles. And that's actually, as I said, a symmetry. I can transform one into the other, but the theory remains invariant under that transformation. So that's called a supersymmetry. Now, supersymmetry was something that people still are looking for in the Large Hadron Collider, but it's certainly true that they would have expected to have found it by now. So it was hoped to be a theory of nature, and the jury's still out. It's still possibly there, but there are various reasons why one would have expected to have seen it by now. So, but my own sort of relation with supersymmetry is not so much related to whether it exists in nature. It's more, as we just said, I'm looking at this very symmetric, mathematically beautiful example of a quantum field theory in order to just understand quantum field theory better and also quantum gravity better. So again, it's like the old spherical cow joke. Does that mean anything to you? Like a physicist having to study milk production somehow. He starts off saying, "Okay, let's assume we have spherical cows," and it's usual. we have to make some simplifying assumptions here and there. So instead of studying the really hard problem, you study a kind of a related problem that's simpler.
Yeah.
And supersymmetry is one of those things that you can add in to simplify various things, so you have a better chance of going further. Obviously, with the hope that then I can apply what I've learned to the actual theory that that is physically relevant.
Yeah, let me ask you about that. 'Cause obviously, you're dealing in pure maths, and a lot of this is hypothetical and thought experiments. You can't actually go to a black hole and do this for a lot of reasons. But do you get to go to CERN or the Large Hadron Collider, and have you done like practical research at places like that?
I don't know. We don't really do experiments as theoretical physicists. I mean, I think back in the day, in the early 20th century, theoretical physicists maybe were doing some experiments as well. But nowadays, it's there's such a large gap. There's a huge spectrum actually. So you've got people at LHC doing the experiment. Then you've got so-called phenomenologists who kind of are quite closely related to the output of the experiments and trying to interpret those. And then you've got sort of various levels of theoreticians in between. And I guess, well, I'm doing it in this direction. You could always do it in that direction. I don't know. We sit at the top, kind of trying to understand the results of all these things and trying to kind of put things together in different ways. So, I mean, I have been to CERN a few times. There's a theory department in CERN.
Wow.
And obviously that you're in the canteen with the experimentalists and stuff. But I'm not kind of going down into the tunnels or directly looking at the experiments and things.
Still, that must be amazing. I'd love to go someday. A really amazing place.
Yeah, no, it's great. Yeah.
I'd have loved to have done physics at university, but I didn't have the maths for it. I think students should be aware that once you get to university level, it is principally maths you're doing. So for most of us, our understanding of where physics is and of these things is through popular writings. And one of the kings of popular writing on this was the late, great Stephen Hawking. And he talked about M-theory as being an answer to everything. I didn't understand it, and even in his popular writings, it's too complex for me. But I saw that you've written a paper on M-theory 7 years ago. So could you tell us a bit about what your research on it was, and just start by outlining what it is for those of us who don't have the maths?
Sure. So, well, I mentioned string theory as the theory of, a theory of quantum gravity, and M theory is pretty much simply synonymous with string theory. So the history is that I said that string theory at some point. I think I said string theory was unique, or anyway, maybe I didn't. But string theory is a unique theory, but it didn't look like that to begin with. It looked like there were, bizarrely, 5 or 6 or so of different string theories. So you kind of go through, again, it's complicated maths. This really is a theory of strings. It's a quantum field theory. Sorry, it's a quantum theory where instead of particles, so a point-like object, you have an extended object, a string. You have a tiny little string, more like an elastic band in some sense. You can have closed strings and open strings, and really, you just take that assumption and then just follow the maths. Combine it with special relativity and so on, and it's really hard maths. But people like Michael Green in Cambridge and so on, they pursued this and found that it only makes mathematical sense. First of all, if you live in 10 space-time dimensions. So this is the kind of the bit I was saying where it doesn't quite relate to the world we live in. But then there are various other requirements. Supersymmetry is one of the requirements as well. And various other requirements. There turn out to be 5 different types that you can get. And then later on, there are these dualities that people realized. A duality is just a map from one theory to another theory, and that says the maths if I map this to this, this to this, this to this, the math is all the same. So anything I can compute here in this theory, I can compute in this theory. And these dualities were discovered and that linked all of the string theories together. And then the collective thing was just called M-theory. Right. There's a sense in which it lives in 11 dimensions rather than 10 dimensions. The M-theory grew, and one of these dualities involves growing a dimension.
And we thought
it does sound kind of weird, but I mean, I want to emphasize that there's kind of a solid maths that takes you this. Well, again, a mathematician might complain it's not all rigorous proven maths that a pure mathematician would kind of nod along to, but it's very convincing mathematics. That gives you this unique theory. So that unique theory is M-theory. So there's a unique theory that we know of that is a quantum gravity theory, and it's called M-theory. And so people obviously want to study this and then try and understand it as much as possible. And my own work on that is, it's sort of again related via this ADS-CFT correspondence. So there's an M-theory relation to a specific quantum field theory, this time living in 6 dimensions, that we could calculate. Again, there's these highfalutin ideas, but then there's concrete, hard calculations that kind of back things up. And a lot of what we're doing is the hard calculations. It's nice being on a podcast because you can talk about all this stuff and it sounds very exciting, and it is very exciting. But a lot of what you're doing day to day are these hard calculations. But they're fun. I mean, for me, they're fun anyway. Fun calculations of new objects. So yeah, we did some solid new calculations in this theory that we don't really know much about. It's kind of a very hazy theory. You know it exists. But the more solid calculations you can do to back up its existence and understand its properties, the better. So that's kind of what I was doing there.
Wow. Yeah, I've not really met many scientists who have published as much as you have. Your research output's pretty incredible. So I'd love to know here, firstly, what are you most excited about in the future of your field? But also, what are the biggest problems to solve? What are the biggest challenges, some of which you might be working on?
Right. It depends on what sort of level you want to answer the question. I guess one thing I really like at the moment is there's this thing called the amplitude, which is so I haven't talked about scattering amplitudes, but scattering amplitudes are the things that you really calculate from quantum field theory, and they correspond to the probabilities of different events in colliders. So in LHC, you smash these protons together, and what's really happening is inside the protons, you've got these gluons and quarks, and they're smashing together. And then there's what's called an amplitude that tells you if 2 gluons come in, what comes out. But actually, in quantum field theory, everything's probabilistic. You don't know exactly what will come out. You know the probabilities that different things will come out. And it's the scattering amplitudes. And so scattering amplitudes are then a mathematical thing. They're basically integrals. And you calculate this integral, and it gives you the probability of whatever event you're looking at. So what happens in the AHC, you bang these things together millions and millions and millions of times, get masses of data, count the number of times that different things happen, compare it with the theoretical prediction from these scattering amplitudes. So these are scattering amplitudes, and then Nima Akani-Ahmed and Jaroslav Trnka about 10 or maybe 12 years ago came up with this amplitude, which followed previous work, where these scattering amplitudes actually turn out to be related to volumes of specific polytopes. And the simplest example of this is really just areas of polygons. So imagine a hexagon or something. And then roughly speaking, the area, it's not quite the area, it's some mathematical property that's similar to area. And if you compute that, you actually get these amplitudes. And it's in this specific theory that I was talking about, this n equals 4 super-Yang-Mills, this special theory. The amplitudes in this special theory are just, in some sense, areas of polygons or higher dimensional generalizations of these. It's totally, you don't give this any information. It's really just a polygon. You're not telling it what particles are in it or anything about quantum field or anything. It's a totally different object, just a polygon. So this is some weird mathematical relation, which I find very fascinating. And and then there's this. Well, the idea is that if you can reformulate quantum field theory in a better way, with maybe this being the germ of a start of it, then you can find a new way of deforming it to sort of get to quantum gravity in a different way. So it's a bit like that, if you think about what happened in quantum mechanics, you have to write Newtonian mechanics, F equals ma. You write it in a different way, with in terms of Poisson brackets and things like this. It's the same theory, but it's written in a different way, kind of nice mathematical way. Once you've got to Poisson brackets, then there's a you just tweak it and you get quantum mechanics. Actually, roughly speaking, you send curly brackets to square brackets. Of course, you have to know what these things mean, but sometimes if you take a theory, write it in the right way, then it gives you a hint of what the new theory is. So there's this idea that we're looking for something new, really. We've got this quantum field theory, we've got general relativity, we want quantum gravity. We do have string theory, which is a quantum gravity, but still, string theory is not of... it's hard to describe this, but quantum field theory is pretty well defined. There's algorithms for computing anything in it. String theory is not as well defined. There's algorithms for computing some things, but not everything. So, we still want something more. And there's this kind of feeling that people have that we are, on the cusp of finding this new big idea. But certainly, another point of view is that, as I started with, we've got these theories and they're too good. We know there's something else out there. Even I've described things from a mathematical point of view, but even experimentally. So I said this agrees with all experiments, but of course there are dark matter experiments. There are things where there's mysterious matter out there that cannot be explained by our theories at the moment. So it's not quite true that it explains every experiment. So there's that. Even from an experimentalist point of view, we know there's something else other than just the standard model and general relativity. So, but from a theoretical point of view, there's a feeling that it should be much more than just a new particle. There should be some whole new way of combining things together. So yeah, we're hoping for that. I'm fascinated by this mathematical relation. I guess I'm fascinated by this theory, this n equals 4 super-Yang-Mills. There's this idea that it might be a theory that you could really solve. So in other words, in quantum field theory, there are algorithms for computing things. Feynman came up with them, Feynman diagrams.
Yes. A
Feynman diagram is an integral, but it's actually just, you have infinite numbers of these integrals of higher and higher, to compute something to more and more accuracy. This idea, and sometimes you do that and you get a very simple answer for the result. So there's this idea that there should be some other way of describing things. So lots of different ideas. If I knew what the big breakthrough was, then obviously I would I would be writing it up right now. But
no, of course.
Yeah, I think just to summarize, maybe there's lots of maybe smaller things that are exciting on a small level, and there's this idea that hopefully out there's this big new idea that everyone would jump on.
Yeah, I find it interesting how the history of quantum physics, it sort of moves in cycles. So we're at about the centenary, I suppose, about 100 years ago now that the new quantum physics was born with Dirac, Heisenberg, Schrödinger, all of that. Incredible time.
Yeah.
I think it's the golden age in the history of science is that 10 years from 1919 general relativity gets proven, and then you have the Big Bang with Friedman and Lemaitre, and then you have quantum physics all happening within a decade of that. It's just nothing like it. But like we said earlier, a lot of those guys then wanted to find a theory of everything, and they all failed. They all couldn't do it. And the Feynman's generation wasn't really interested in finding a theory of everything. They wanted to find all the subatomic particles. And then we get round to sort of Penrose's generation that you mentioned earlier, who are interested in the big questions again. So I suppose these things move in cycles as to what people are most interested in doing. But
right.
But we're in an era of quantum computing now and being able to do practical stuff with it, which blows people's minds. So I'd love to ask you here why, the floor is yours, make your case. Why should young people, new students, take up particle physics and high energy physics at university or go to weekend and summer courses to study this stuff?
Well, I mean, hopefully I tried to convey some of the excitement. I mean, for me, it's, you're studying the fundamental laws of the universe. I mean, what could be more exciting than that, really? You can do it, as we discussed earlier, I'm not directly doing experiments. The experiments are kind of there in some sense. As we said, these theories agree with all the experiments we know. Obviously, there are new things coming online. There's some mysterious issue with dark energy just recently that may hint at some major breakthrough. But the experiments are there, and then there are theories there, and then the question is, can I kind of get some bigger theory that agrees with those theories in the limits, but solves the other problems? So it's all mathematical, if you like. I use a pen and paper and a computer, basically, and a blackboard if I'm talking to people.
Yes, it's a very massive blackboard.
So that's very exciting. I think people who learn about it, I mean, I guess I would be, on the one hand, I want kids to sort of know about this stuff and learn about it and be excited by it. And I think people who get to a certain level of knowledge are inevitably, if they're that way inclined, inevitably will be excited by it. But there is that caveat that I hinted at before, and we've said a couple of times. It is really hard. So keep, I struggle a bit with PhD students and when they're going on to postdocs, and there are people who do a postdoc after postdoc and then end up not with a permanent position, and there it is difficult. Personally, and also, as I also mentioned, you have to also like doing the nitty-gritty incremental bits, because you're not going to be there being the next Einstein. Well, maybe someone is who's listening, but not everybody will be. Not everyone will be coming up with this massive new idea. So you have to understand that you're working in that area, but you're also at the cliff face doing the incremental hardcore calculations as well.
Yeah.
So I don't want to kind of oversell is what I'm saying, but I think people who are who get the idea will inevitably, people come in and ignore what you're saying about the next Einstein and want to carry on working on it. So it's a mixture of both.
Yeah, we're often interested in sort of the explosive dramatic stories in the history of science, but a lot of it is just the day-to-day, week-to-week grind.
Absolutely, yeah.
When we were recently talking to Phil Halper, he talked about how some of the new telescopes and probes were informing a lot of data around these big things. And we've mentioned it not being experimental, but in many ways, the whole universe is your lab. You can observe what's happening in the middle of stars and galaxies and things like that as your data. Has much of your science been informed by recent developments, by telescopes and probes and that sort of thing?
So, well, not really directly, as I said, because they're not. I mean, a lot of what they're doing. I mean, there's lots of stuff that people do, right? People want to understand how the sun works, for example, and people study how galaxies form and so on. Now, a lot of that nobody thinks is new fundamental physics necessarily. It's just understanding how the physics we know works in that particular situation.
Right.
Now, of course, there are exceptions. Dark matter being the obvious one. People study galaxy rotation, and it's not working how it should do if the stuff that we see is all the stuff that's there. And so you can induce that there's some stuff that we can't see that's actually spherical rather than in a flat galaxy shape. And then another one, maybe you were hinting at that, is this recent studies. Again, I'm not so clear on the details, but on the expansion of the universe. So this is to do with the dark energy. The simplest explanation for dark energy is this cosmological constant, which is this extra term that you can put in Einstein's equation. And that was always a mysterious explanation, just because it has to be so incredibly small that non-zero. But people first thought it was zero, which is kind of fine. Okay, zero is not maybe a difficult thing to explain, or you just say, okay, it is. But then if it's going to be non-zero, then why is it so very, very close to zero? But now these new experiments are suggesting that it's actually not even constant, and therefore it's not a good explanation even right from the start. There needs to be some other explanation for that. And that's very exciting, because that could be something genuinely new that needs explanation. So they're the sort of things that I guess the more theoretical fundamental people are sort of looking out for as genuine new stuff. But again, also from the more mathematical side that I'm on, it's really understanding the maths of some of the theories that we already have, and how to kind of try and get a theory that combines general relativity and quantum field theory. And that, to some degree, is a little bit independent of. It's not independent of experiment, because of course loads and loads of experiments have gone into getting to quantum field theory and general relativity in the first place. But now we've got those. I know those are there. I know they're right in the limits that they work, and I want to try and understand a theory that can combine them. So that doesn't necessarily directly rely on any new experiments, if that makes sense.
Yeah, I got it. Well, thank you so much for your time and your insight today. If people want to find out more about you or your research, where could they go?
Well, I mean, I'm very happy to accept emails if anyone wants to email me. There's a website on Durham University that has there's my homepage there.
Yeah.
And you can find my email address there.
Yeah, and all 90 of your publications if they want to read. Terrific. Well, I really appreciate your time and your insight. It's mind-blowing stuff. A lot of it way out of my league, but it's really, really interesting and fascinating. And I hope more people who are watching this will look to go deeper into mathematical physics. Professor Paul Heslop.
That would be great. Yeah.
Yeah. Thank you so much.
Thank you very much. Thank you.
Thank you so much for watching. Don't forget to like and subscribe. Stay tuned for more amazing conversations with incredible researchers who are changing the world we live in and driving humanity forward. Feel free to check out my Instagram at polymath_Sam, or go to my website at www.sam-McKeePodcast.co.uk.